Hello, my name is Bajor Edrees,
And I'm Matt Bajor.
and in the following video we would like to explain to you the operation of our high dynamic range photodetector IC that we designed and fabricated for Professor Peter Kingett's Spring 2014 VLSI Design Lab at Columbia University.
In this project, we designed a photodetector integrated circuit that offers the potential for high dynamic range operation by digitizing light output at the pixel level. The design was carried out using the 180 nanometer IBM 7RF technology development kit. In what follows is a brief account of the design process and some simulation and measured results. The use of image sensors presents several limitations for visible light spectrometers. Both CCD and CMOS one-dimensional imagers typically use a global shutter, which is activated for a fixed time period determined by the control electronics. After the image is captured, each individual photodetector element is serial read out of the system through a multiplexer and shared charge amplifier. This process is time-consuming and also relies on an estimate of the incoming signal to set the amplifier gain and integration time to avoid saturation of the brightest pixel. This effect also limits the dynamic range of the system. The nominal dynamic range is quite large for the Taos AMS 1401, which is shown below. For the example, more than 1,000 to 1 range can be achieved within a single exposure, and the exposure duration can be modulated over a further 3,000 to 1 range. If the exposure time is incorrectly estimated or the difference between the bright and dark pixels is large, however, the net dynamic range is compromised and the full range is not realized. Overexposure or saturation can also lead to blooming and contribute noise to neighboring pixels. With our circuit, we are able to simplify and improve the current photodetector design using the following methodology. This is the basic schematic of one pixel. Incident light is sensed using a reverse bias CMOS photodiode. The photodiode can be modeled as a current source representing charge generation from the incident light and a parasitic capacitor, corresponding to the diode junction capacitance in parallel with the current source. The capacitor is initially charged to the supply voltage VDD, and the reset transistor is open-circuited. Incident light causes the capacitor to discharge, and subsequently the capacitor voltage decreases. As soon as the capacitor voltage crosses a threshold VREF, the comparator block switches low. The switching output of the comparator passes through an inverting buffer and turns on the reset switch. The reset switch charges the capacitor back to VDD. As the capacitor voltage increases, the comparator switches high. Once again, the switching output of the comparator propagates through the inverting buffer, and after some delay depending on the buffer capacitance, the reset switch is open-circuited once again. Subsequent illumination of the diode repeats the above cycle. At the output node, pixel output, a pulse edge is observed. As a result of this operation, the circuit converts a quantum of incident light into a pulse train. The intensity of the incident light is encoded in the frequency of the pulse train, with larger frequency corresponding to higher illumination intensity and vice versa. As we previously mentioned, the core of each pixel circuit is the integrator comparator block. The integrator integrates the output current of the photodiode over a specified integration time. Once the output of the integrator crosses a threshold set by an external analog voltage reference, or VREF, a count is triggered in a digital counter and the integrator is reset.
For our design we included a number of different photodiode structures. By varying the geometry, shown on the left here, we used two different geometries, the fingered and the non-fingered geometry, and by using different dopant structures, as shown on the right. This allows us to address different trade-offs between sensitivity and parasitic dark current in the photodiodes.
Our IC design was divided into 5 parts. Experimental diodes for characterization, 32 switchable pixels, diodes, and decoder, 7 pixel bank, diodeless test pixel, current distribution network, and decoupling capacitor. Our PCB was developed over 2 iterations and is used for testing and obtaining reproducible results. Our IC is mounted in the middle of the board. In the lower left is the DC input connector. Also on the board is a 1.8 volt regulator IC and decoupling caps.
VREF, CREF, and I bias are all adjusted using potentiometers. At the top are two input connectors providing test, output, and control points.
Shown here is our photodetector chip test bench. The photodetector IC is placed into a breadboard, which is in turn mounted on a precision XYZ stage. This allows us fine manipulation of the individual photodetectors underneath laser illumination. The optics setup shown here above the die consists of a beam splitter that accepts laser illumination from a diode laser shown on the right and relays this illumination to a camera for imaging and to the individual photodetectors for probing. Shown in the camera image here are 7 individual photodiodes under laser illumination. We will now vary the intensity of the laser illumination and observe it in the camera footage. Now we've reduced the laser current, reducing the laser intensity. And in this frame, we've increased the laser current, causing an increase in the laser intensity incident on the photodetectors. Shown here is the oscilloscope output of the pulse train from an individual pixel. As we increase the laser current, i.e. the intensity on the photodiodes, you see the frequency of the pulse train increase. Decreasing the laser current produces the opposite result, and you see an increase in the spacing of the individual pulses, i.e. a lower frequency. To further quantify the frequency output of individual pixels, we connected the outputs to a digital frequency counter, shown on the top of the screen. As you can see in the middle of the screen here, we are adjusting the laser intensity by adjusting the current input to the laser diode, and you can see the frequency increase with increasing current. Right now we are at 100 milliamps of current, and the frequency is in the vicinity of 2 megahertz. By decreasing the current to 10 milliamps, you observe the frequency fall to 6 kilohertz, thus showing the shift in frequency with varying intensity of the laser diode.